This video goes over the first part of lesson 7.3, and lesson 7.3 is all about proving that triangles are similar. Our essential question is, how can you prove that two triangles are similar? There's three different ways that we can prove triangles are similar. The first is the angle-angle similarity postulate. And you can abbreviate this postulate when you use it in your explanations, or if you write a proof, you can use just this AA similarity like this. Remember that little squiggle symbol right there means similar. So angle-angle similarity is AA with this symbol. And what this postulate tells us is if two angles of one triangle are congruent to two angles of another triangle, then the triangles are congruent. Let's add some markings to the diagram here, and then we're going to write a similarity statement. So maybe we have angle A and angle D congruent. And then let's just say angle B and angle E are also congruent. Congruent angles are going to be marked with the congruent angle markings. You can also often find congruent angles using properties of parallel lines. For example, corresponding angles or alternate interior angles, or even vertical angles. Those can give you a pair of congruent angles, or they can just be given or marked already in the diagram. So now that I've marked my diagram, you can write a similarity statement. You just want to make sure that you follow the same pattern in each of the triangles. So if I call my first triangle ABC, angle A matches with angle D. So I need D to be the first letter. And then B matches with E. And then F. And then for the bi, we say angle-angle similarity. So we write the similarity statement and then we justify it with the similarity postulate. The second way that we can prove two triangles are similar is the side-angle-side similarity theorem. We'll abbreviate this as SAS with the similarity symbol. This theorem tells us that if an angle of one triangle is congruent to an angle of another triangle, and the two sides that include the two angles are proportional, then the triangles are similar. It's really important that the two sides include the angle. Another way that you can think of this is that the angle must be between the two proportional sides. So let's go ahead and mark up our diagram here. It's going to be helpful probably in this section. If you have colors, you might want 3 colors. I guess in this picture, I'll only need 2, but for the next one, we'll need 3 colors. So I'm going to mark segment AC in green. And I'm going to mark its match here, DF, in green as well. And then I'm going to mark CB and FE in blue. And then I need the angle in between those sides to be congruent. So angle C congruent to angle F. Here's what we have. So in the diagram, we have angle C is congruent to angle F. And then the sides, notice I didn't mark them congruent. The sides aren't congruent, they are proportional. So we could say something like AC over DF will be equal to BC over EF. So they're in that same ratio, they're proportional. And then we can write a similarity statement. It's the same statement as above because it's the same triangles. So triangle ABC similar to triangle DEF, but this time it's by SAS similarity. There's one more way that we can prove triangles are similar, and that's the side-side-side similarity theorem. We'll abbreviate this as SSS similarity. This theorem tells us if the corresponding sides of two triangles are proportional, then the triangles are similar. I'm again going to use color here, and this time there's 3 sets of proportional sides, so I'm going to use 3 colors. So I'll go with the same colors as above. And then we will also add in the last side, so A, B, and D, E. So this time, all 3 sides must be proportional, which means AC over DF must equal BC over EF, which must also equal AB over DE. And if that's the case, we would be able to write our similarity statement and say triangle ABC is similar to triangle DEF by side-side-side similarity. Now that we've discussed all 3 similarity theorems, let's go ahead and look at some examples. We're not going to write a formal proof here. We're just going to explain why the triangles are similar and then write a similarity statement. Notice that the 2 triangles that are given in the diagram there only have sides. They don't have any angles. So my guess here, just looking at the picture, is that it's going to be side-side-side similarity. But we need to show our work to kind of justify our things. So let's go ahead and start with the ratio of 2 sides. Now you'll notice too that there's like some shorter sides and longer sides. So for my shorter sides, I'm going to match up GE with CA. And when we do that ratio, it's 8 over 6. And then if we divide that by 2, we can reduce it to 4/3. Similarly, we can also do the second shorter side. And that would be side FG over BC is equal to 8 over 6, which once again is equal to 4/3. And then we have one last side to check. So I just did my shorter sides. Let's go ahead and check the longer sides. So the longest side in that first triangle here is 12, and the second triangle is 9. So I have EF over AB equals 12 over 9. And then these are both divisible by 3, so we can reduce that to 4/3. So you'll notice that we have all 3 sides. So I have an S, an S, and an S. So now we can write our similarity statement. And I'm going to name the first triangle, triangle GEF. You can really name the first triangle whatever you want. Just make sure that you follow the same pattern in the second triangle. And that's where the colors are really helpful. So in my picture, GEF goes from the 8 to the 12, and it's the blue and green sides. In the other picture here, it would be CAB. That's blue to green. And then the Y, I'm going to justify it with the similarity, side-side-side similarity. Here's another example where we're going to explain why the triangles must be similar. The first thing that hopefully you notice is that there's 2 parallel lines, or 2 parallel segments. We have segment PT is parallel to segment SR, So what that means is we can find some things like alternate interior angles. So as an example, angle T and angle S, if you look at these as the parallel lines and the transversal, there's your kind of Z shape. You're on opposite sides of that. So we can say that angle T is congruent to angle S by the alternate interior angles theorem. Then you can get a second set of angles. There's a couple different options here. Sometimes there's more than one way to show they're similar. I could get another pair of alternate interior angles, but I think it's maybe going to be a little bit easier if we just look at the vertical angles right here that I'm marking in purple. When we name these two angles, it would be best if we use 3 letters because there's multiple different angles that have a vertex of Q. So when I name the one in the smaller triangle on the left, I'm going to name it angle PQT. And that is congruent to, and then if we follow the same pattern, notice how PQT goes from the unmarked angle to the 2 marks to the 1 mark. If we follow the same pattern, that would be RQS. And that's by the vertical angles theorem. And just like that now, we have 2 angles. So we can conclude our proof of therefore, and then for the similarity statement, remember that you can name the first triangle whatever you want. Sometimes on the CYU, I'll already name the first one for you. So I'm just going to name the first one PQT. And then if we name the first triangle PQT, we would want to name the second triangle RQS. And that is by the angle-angle similarity theorem. And that completes our little mini proof. So there's my angle, there's my angle. I've established there's 2 congruent angles. Therefore, the triangles are similar by the angle-angle similarity postulate. Let's try another example. This one is kind of cool because the 2 triangles that it's looking at are kind of right on top of each other. So it's often helpful to draw them separate. So if we look at the little triangle, I will draw that right here. And then I'm going to put the letters back in. And then, so that's JKL, the first one, in blue. And then the second triangle, I'm going to outline in red here. That's the bigger one. So we have triangle. And then it has JMN. And then we have to use the segment addition postulate to get the length of this side is 2 plus 4, so 6. This side is 3 plus 6, so 9. So I have a 6. I have a 9, and then the trick for this problem is that the triangles overlap, and they both contain angle J. Well, angle J is congruent to itself by the reflexive property. So if we start to kind of go with our ideas here, since we have 1 angle and 2 sides, I'd probably make the prediction that it's going to be an SAS similarity. Let's start, though, with the first one. So I'm going to start with the first pair of proportional sides. So notice that JK over JM is equal to 2 over 6. And if we divide by 2, that is equal to 1/3. Next, we have angle J that's congruent to itself. So angle J is congruent to angle J by the reflexive property. of congruence. And then let's check the other side ratio. That is side JL over side JN. And that is 3 over 9, which if we divide by 3, also reduces to 1/3. So there we've established that we have a side, we have proportional sides, and then the angle that's in the middle is also congruent. So we can write our similarity statement and say something like triangle JKL is similar to triangle JMN by side angle side similarity. For our final example here for the day 1 portion of the notes, it's a try now, and you're going to look at the triangles and explain why they're similar and write a similarity statement. For the explain why the triangles are similar, this is where you're going to have your choices of the 3 similarity postulates. Either angle-angle similarity, side-angle-side similarity, or side-side-side similarity. All right, now the trick of this problem is to find the measure of angle C using the triangle sum theorem. So let's just do a little scratch work here. The triangle sum theorem tells us that the angles in a triangle add to 180 degrees. So if we look at this right here, this triangle is 180. Well, we have total 180. Let's subtract out the 90-degree angle that's right here and the 43-degree angle right there. And when we do that, we're going to get 47. So the measure of angle C is 47 degrees. So I'm going to start there in my little kind of explanation here. Measure of angle C is equal to 47 degrees, and it's by the triangle sum theorem. And since angle C is 47 degrees and angle F is also 47 degrees, we know that angle C is congruent to angle F. Next up, there's a second set of congruent angles because angle B and angle E are both right angles. So angle B congruent to angle E, and the reason is because all right angles are congruent. And just like that, now that we have 2 pairs of congruent angles, we have an A and a second A, we can say, therefore, triangle ABC is similar to triangle, and then careful, ABC, the 43-degree angle would have to go here, and that would match up with ABC is 43 to 90 to 47, so going that same direction, 43 to 90 to 47 would be triangle DEF, and the reason is by angle-angle similarity. This concludes lesson 7.3 day 1. Thanks for watching. Bye.